This was problem number 39 from chapter 12, section 2 on page 525. And we are supposed to solve this thing. And it's Kayla, that's right. The hint I gave you last time was that if you had something, it's not too dark. If you have something like this, 2 to some power equals some number, let's say 2, well, then you'd know that whatever goes into here would have to equal 1, because that's the only way for that to work out. And so if it happened to be something like 2x minus 1, then we would have 2x minus 1 equals 1. Now, I think I did something like this also last time. I said you have 2 to some power equals 1. What must that power be? 2 to what value equals 1? Yeah, 0. That's the only way to make that work. And so, let's think about this. Is that different if we change it to a 3? 3 to what power equals 1?
0.
It has to be 0. And so that's what's going on here. The only way to make this work is if whatever goes into the power is 0. And so what this tells us is that this stuff that went in has to equal 0. And so that gives us 2x squared plus 5x minus 3, 0, which do not leave it alone. Leave it alone. Thank you. So I'm willing to bet that we could factor this guy. Right now, I'm just kind of blindly going along and just saying, well, I'm just on autopilot right now, right? I kind of went along and said, okay, that thing equal to 0. Oh, I'm just solving it because that's what I do, right? Like it's autopilot. I'm betting that we could factor this. And the first thing has got to be a 2 and an x if it does factor, because that's the only way to factor.
I have a quick question.
Yes.
Is that a plus sign or is that a multiplication sign? I can't
Where?
see. 2x squared.
It's a plus.
5.
That's a plus.
Sorry.
Yep. I mean, I just copied down the original problem.
I thought that it just looked like a multiplication sign to
Well,
me.
no, good. Thanks for asking.
And then I panicked because I thought I wrote it down wrong.
Okay, cool. So I'm guessing, and then a 3, because one of these is going to have to be a 3. I'm willing to bet it's this one, 3 and a 1. Outer and inner gives me a 6 and a 5. Yeah, or a 6 and a 1 will give me a 5. And I guess I'm going to need that one to be positive, and so that should do it. So that means that x equals what, or x equals what?
X equals -3, right? Or
Yes, x equals -3, or
hold on, let's see. 1/2.
1 positive 1/2. Yeah. And I'm not going to go through and check this, like, because I feel confident that we did this factoring the right way, but I'm willing to bet it works, that if I were to take that value of x, 1/2, and plug it in right there and right there, then I evaluate that thing and it should come out to a big fat 0, in which case we will have 3 raised to the power of 0. 3 raised to the power of 0 is indeed equal to 1. And so that should solve that equation. Ditto with this guy right here. That should all work out. Now, this is one way of thinking about this. And this is the way that you're probably, well, shortly we're going to learn even better methods, just even more just Like when I got to this point, I didn't use my brain. I just went into autopilot. There's an autopilot way of taking care of anything with exponents or equations involving exponentials. That's where we're going with all of this. But for right now, this is one way of dealing with this type of equation. But in general, there's a really nifty tool to use, especially if you're just stumped on something. Let me show you what that is. So you have some kind of equation. So are you good with the explanation up until there?
Yeah.
Everything good? Okay, any questions before we go into this slight tangent, but it actually comes into play for something you're going to be doing in your homework. So I figured we should roll with it. So we're good to go?
Yep.
Another way of thinking about any equation, like you have some equation that you're trying to solve. Yes, this one's a little funky because you have all your stuff over here, and then this is just one single number over there. That's cool. The idea is this. You look at your equation and say, well, you know what? We could think about this on the right side as being some function. It's just some function. You put x's in and you get x's out. That's cool. I mean, you put x's in and you get some number out. That's cool. And then what's over here, yeah, there's no x involved, but you could still think about it as a function. G of x equals 1. What does that look like? Well, it's just a constant function. 1, right? If I wanted to graph the function g of x equals 1, we've talked about this. This is just a line that happens to have 0 slope, right? In fact, you could say this is in the form mx plus b. It just happens to be that m is 0 and that b is equal to 1. And so it's just a flat line. So I don't think I've said anything new there. I'm just going to kind of gloss over that point. But the idea is this, that you have some kind of function, or yeah, I'm sorry, you have some kind of equation that you're trying to solve and you don't know what to do. This is a really good principle. You could just say, well, you know what? Why don't I treat this thing as just a function in and of itself, and I'll plot y equals f of x. And then I'll treat this thing like a function in itself, and I'm going to plot y equals g of x. So I'm going to plot these two things on the same graph. Axes. I'm going to plot them on the same axes. And then you say, I can't plot that, and neither can I. I don't know what it looks like. So you guess what I'm going to do? We're going to go to Desmos. And so let's get this going. All right, can you see my screen?
Whoa.
Yeah, that's what that thing looks like. So I took the left-hand side of the equation and said, let's just pretend it's a function just by itself. And I said, okay, so then it's a function f of x equals 3 to the power of 2x squared plus 5x minus 3. I plotted it. That's all I did. Now I'm going to say, okay, the right-hand side of the equation is another function. And let's see, we'll call it y equals, oh yeah, 1. Yeah, that was an easy one. And I could see, this is what's really nice here, is right away I could see I'm not on a wild goose chase here. There is at least one solution to this thing. And so this is a nice principle to use just in general. Like when you have an equation that looks crazy, something that you've never seen before, and you're kind of going like, what is going on here? At least doing this can give you a sense of like, okay, there should be solutions. Because the left-hand side of the equation looks crazy, but the right-hand side of the equation isn't, whatever. But the point is, there are places where the left-hand side is equal to the right-hand side. And these are these intersections right here. And it even tells us where it is at -3 and 1. And then over here at 0.5 and 1. And isn't that exactly what we found? So that's nice, right? And this is one way of, it's a bunch of things. Can I stop sharing now? You got this picture in your head for the rest of your life and forever and ever. Right. So that's the idea, right? You have some crazy function f of x, you don't know what's going on. And maybe the other side of your thing is also crazy. Who knows? So we plot both of them, and then we do that on the same axes, and we could see, aha, there are intersections. I can expect solutions here. And sometimes we get really lucky, like we did just then, where it wasn't approximated. It gave us the exact answers. It gave us -3 and +1/2. Sometimes these will come out to be approximate, whatever, but that's how you could take an equation that's really funky, right? And something you've never seen before, and try to at least get some kind of approximation or solution or something like that. In your homework, you're going to have not equations, but inequalities. And so we'll go ahead and talk about this right now. And it does indeed say to solve by graphing. So here is number 40 from page 528. It says to solve by graphing. And it gives us 3 to the x is less than or equal to 1. And so I'm going to do the same thing here. I'm going to say, okay, this is like we have two separate functions. One, the function on the left, and we want to know when is that less than or equal to the function on the right. And so what I'm going to do is graph both of them. Are you following along thus far? Any questions? Do I need to slow down, speed up?
Just one. Whoa, hold on. Okay.
Okay. So again, they told me to solve some relation. It's an inequality. Solve by graphing. And I said, okay, what we're going to do is pretend that this is a function, and I'm just going to graph it. That this is a function, and I'm just going to graph it. So 3 to the x, I don't need to use my brain. 3 is bigger than 1, so this thing shoots up. This is the function 3 to the x. I'm going to go ahead and get one interesting point right here. Where does that go through the y-axis? What value? At 1. There you go. Oh, that happens to be where that one also goes through. So that's nice. In fact, I'm going to do this one in green. I'm going to say g of x, my other function, is just 1. It's the constant function g equals 1 or y equals 1. And it happens to go through right here. There we go. Nice. And so it's asking us for what x values is the red function smaller than or equal to the green function.
Okay.
And so you tell me, what x values make this true?
Can you say what you just said before? I'm sorry.
Yeah, we are looking for the input values of x, which make the red function smaller than the green function.
Okay.
So we could say where, this is kind of, I like to think of where, meaning where on the x-axis. Is it true that the red function is less than or equal to the green function?
X has to be less than or equal to 0.
Yes. And so what I like to do, I'm just going to think about it this way. Because I've already drawn this out. In fact, it says solve by graphing. I have to do that. I'm going to say, like, my first thing, it's almost easier in this case to say, well, it ain't true over here. the red is bigger, right? That thing is bigger than that. So that ain't gonna work. I'm gonna find where it's equal. It's equal here. So that is a solution. That does make that true. So we're gonna include 0. There's 0. And I can see it's true all the way down there. And so I'm gonna say all of these values right here and all the way down forever and ever. And so what that is the interval negative infinity up to and including 0. And so the solution to this is, well, we could put it as x in this interval. So in other words, whenever x is in that interval, it will be true that 3 to the x is less than 1. Let's just check ourselves here. Let's just make sure that that's the case. Let's choose any number from in here. How about -2? -2 is a number in that interval. And my solution says that if I take that number and plug it in, this thing should be true. So let's check and see if that's the case. If I take 3 to the -2, we are wondering, is it true that that is less than or equal to 1? How do we rewrite 3 to the -2 without that negative exponent?
Gosh. Just a second. One over 3
Yes.
to 2.
There you go. Good. That's all a negative exponent means. So it's a fancy way of saying just denominator. And so, okay, that is 1 over 9. Is it true that 1 over 9 is less than 1?
Yes.
Yes. Okay, so yeah, I feel good about this answer. And from the graph, and really that's the point of this, from the graph, I could tell that, yeah, if I plug in anything over here, and now I can kind of see that, right? Plug in a 0, you get out a 1. Yeah. If it's less than that, you've just taken 3 into the denominator. Oh, yeah. 1 over 3 to something has to be less than 1. Okay, so we should be good to go. That's that. Any questions on this? You're going to have 2 of these in your homework.
I don't think so.
Okay, good. So that's the idea. And it was really nice is that you had a question about this idea that led us into the idea of, I have something I have no idea what to do with. You could graph it, right? And in the case that it's an inequality, you're probably going to get a set, like an infinite set out of this. And by infinite, I mean an infinite number of points, not necessarily that you're going to have infinity in there. But there are infinitely many points is what I mean. Anyway, who cares? You're probably going to get a set of infinitely many numbers when you have an inequality. And we've seen that a bunch of times. If it's an equals like we had in the homework, you might get multiple solutions or whatever. You might get one solution. You might get no solutions. That's also possible. So, for instance, real quick. They said solve by graphing, when is 3 to the x less than or equal to -1, we would do the same thing. We would say, well, this is what 3 to the x looks like. It goes through here at 1. And it's asking, when is it less than or equal to the line -1? I'd say, well, that's never the case. 3 to the x is always bigger than -1. And so in this case, we'd say it's no solution. It's the empty set. There's a bunch of different ways of doing that. There's the empty set, or you could just say no solution. At any rate, I don't think they're going to give you anything funky like that. Yeah. Okay, so it's in your homework, you're going to have one with an exponent. You're also going to have one with a log. And that's why it's really nice to be able to draw a log or graph a logarithmic function. Well, very helpful. Okay, so can we move on? Are we good to move on? I've not been recording. Oh, I have been recording. Good. Okay. So are we good to go?
Yeah.
Okay. So let's see the topic for today. There's three things we got to get through. First off, we talked about this last time. We said that there are two ways of writing something like this. We have some number A, right? A is a positive number. And we're going to raise that to some power. So we have, again, let me just identify the different parts of this right here. We call that number that's being raised to a variable. We call that thing the base. Okay. And this thing, in this case, right, when you have something that looks like this, we call this an exponential function. This thing that's in the exponent, in this case, is the input variable. And then the thing that you get when you compute it. So like, let's say we had 2 to the x, and we actually went in and plugged in some value of x, like 3, we would get some number. 2 to the 3 happens to equal 8. And we'd say then that is the output value when and so we have this relationship. We have inputs, in this case, x, outputs, in this case, y, and we have the base. And we said last time, and I said this is going to be really important to be able to go back and forth between these things, but we said this means exactly the same thing as log base A of the output is equal to the input. So there's two ways of writing this equation right here. We could either say that 2 to the third is equal to 8, or we could say the exact equivalent thing. They mean exactly the same thing, that log base, and look at what's happening here. The base is the thing that goes in the little subscript here. And so when I'm looking at this and I'm going to translate this into a logarithmic equation, I could say, well, the base, that's the first thing I identify. I just look at this equation and say, okay, what's the base? 2's the base. Okay, so let me do that. And now we're basically swapping the roles of input and output. And so what goes in here for this equation?
Sorry, just 8.
8. And now what's the new output?
3.
3. That's it. That's all it means. This is a fancy way of writing this thing right here. And this works for, well, everything. I mean, like, they mean the same thing. They really do mean exactly the same thing. One looks really funky. One is less funky, but you've been exponentiating things for a long time now. And so it's a bit more intuitive. But this is the idea. And so part of your homework's going to be translating back and forth between these. They're either going to give you an exponential function. They're going to give you an exponential equation and tell you to write this as a logarithmic equation. Or they're going to give you a logarithmic equation and tell you to write it as an exponential equation. And so let's do a couple of those to get the feel for this. So I'm going to erase it. Can I erase this stuff here?
Yeah.
All right. So here's a couple of examples. And if and when you get messed up or you're not sure what to do, just use this and replace symbols where needs be. So here's a couple of examples. We're going to do, okay. So we want to write this as a logarithmic equation. And so you tell me what to do. What do I need to write?
Okay. Um, 25 equals 5 squared. Okay, so you have log base 5
Yes.
times 25.
There's not times anything.
Or no,
You're not
the parentheses.
multiplying anything here.
Yes.
You are not, there is no such thing as log 5. That is not a number. You are not doing log 5 times some number here. That's not what that means. This is a function. This entire thing, log base 5 of something, means this is a function that's an input-output relationship. And whatever you put into here is the same as putting into your function right here.
Right.
Okay? Okay.
I misspoke. I know it's not times.
Oh no,
forgot.
sorry, my thing is going crazy now. I don't know why all of a sudden it's telling me that we have only 40 minutes left. I don't know.
My Zoom was doing that too, but I don't have premium and I never have had
And
premium.
I've never had premium. Maybe this is something that they've changed recently.
I
Like
have a
as
feeling
of
this is
now.
a new update or something.
I don't know. Well, when they kick us off, we'll get back on. So I'm not scolding you. I am scolding you because this is so important. And I know that what probably you were just looking at it and just reading it the way that you've been reading it forever. This times that, like I get it, but it's such an important point. I've had so many students who have not gotten that this is we're inputs and outputs, and so I just had to make a big fuss of that because it is one of the most important things. So okay, what's the input?
25.
25. And what's the output?
2.
Yes. So this means exactly the same thing. This means if you take 5 and raise it to the power of 2, you will get 25. Which is true. It is true that 5 squared is equal to 25. Okay, let's do another one. Let's go in the opposite direction. Let's go log base 6 of 216 equals 3. Write that as an exponential equation.
Okay.
Okay.
So 216 equals 6 cubed.
Yes. Yes. And I think that's correct. I did that one earlier, and I think that I multiplied 6 times 6 times 6 correctly. But yes, that's exactly what this means, right? So when you see something like this and you go, oh, what does that mean? You could always just say, wait a second, this is hurting my brain. Let me just take a second and do this. Oh, okay, that's what that means, because I have a much better feel for what this means rather than that. So, okay, let's do two more crazy ones. Here comes a crazy one. I want you to translate this into an exponential. That is a B as in boy, as in Bravo, log base B of V as in Victor equals W as in whiskey. That is the International Phonetic Alphabet, by the way. Bravo, Victor.
Whiskey?
Whiskey. Whiskey is the one that you see when you're on a radio. You're saying, whiskey too. That's, yeah.
Interesting. Okay. So V equals B to the W.
There you go. There you go. And we don't, and just like whenever you see something like this, remember, this doesn't necessarily mean that this has to be one number. This could be an entire expression, right? V could be, like earlier, it could be something like 2x squared minus 5x plus 3, or whatever it was that we had, right? Like any one of these could be a big, ugly expression, but we could kind of stop and say, well, wait a second. You know, like in our problem earlier, 3 raised to the 2x squared minus 5x or plus 5x minus 3. It's like, well, wait a second, just shut up with all that plus x's and squareds and stuff, and we'll just call it w. And then if we had something like that, we could say, well, whenever w happens to be, no matter how ugly it is, we could rewrite it, boom, like this, or vice versa. And either way can be helpful. And so, like I was just saying, a raised to the power of 2x plus 1 is equal to b. Please rewrite this in log form.
Okay.
Okay.
So you have log base b. Wait. No, I'm looking at this wrong. Log base. Wait.
What's the base? A, right? Because just think about it. It's the base, and this is what should be going through your head every time you look at one of these. In fact, this is my first question. No matter what side of these I'm looking at, the first question I ask myself is, what's the base? And so when I look at this, I go, what's the base? Oh, 5's the base. I look at this and go, what's the base? What's the 6 is the base. What's the base? B is the base. In this case, what's the base? A is the base. And so this is, tell me.
A.
Log base A of what equals what?
Okay. Oh my goodness. Of B.
Of B.
Equals 2x plus 1.
There you go. That's exactly what this means. So given either one of these, we could say, well, maybe it's easier in our situation to use this. Maybe it's easier. Like, and if the idea were to get x by itself or to solve for x, it might be easier to do this and then subtract 1 and then divide by 2. And lo and behold, we would have x by himself. It's something we're going to get into a little bit later in a few more days, but that's the idea, right? Like I was saying, really the important thing is you identify, if you haven't, well, in either case, you identify what's the base, what number is being raised to a power. In this case, it's 6. In this case, it's 5. In this case, it's B. In this case, it's A, right? And then we're saying, okay, what are my inputs and outputs? And then we're just switching the roles of inputs and outputs. That's all we're doing here. It used to be you plug in a 2, you get out a 25. Now we're saying, well, if you plug in a 25, you get back your 2. This says, and we're going to think about this as an input. This says when you put into 16, you get out a 3. This says when you plug in a 3, you get out a 216. It says you plug in a V, you get out a W. This is just backwards. It says you plug in your W, you get back your V. It says when you plug in a 2x plus 1, you get out a B. It says if you plug in your B, you get out 2x plus 1. Kind of come back to where you started. So you're going to have a bunch of these. None of them are going to be as bad as this, or I don't even think as bad as this right here. But this is you're going to have a bunch of those. So, okay, now, okay, you ready to really break your brain? Okay, so, am I good to erase?
Yeah.
All this, okay, so kind of like what we did last time, we're going to, what do you have? Oh, you can play with that, that's fine. We're going to work by analogy. We're going to think about a certain function. A function that we've played with before. And I'm going to put x there. We're going to do that. The function that we're working with is x cubed. It's the function that says you take your input value, let's say 1, you cube it, and you get out whatever that number is cubed. 1 cubed is 1. What is 2 cubed?
8.
8. Good.
Clang, clang, clang. Clang, 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 clang.
And we're going to stop there. I'm going to stop there for right now. Now, okay. So, oh, I wanted to ask that first. I should have looked at my notes before I started this. Okay, I wanted to ask you 2 questions before we did this. First off, forget that we did this. You're not allowed to look up here or at your notes where you wrote that down. What is the cubed root of 8?
2.
2. Okay. I believe you. What is the cube root of x cubed?
X.
X. In other words, you know, right? You have the sense that this is your output of something, right? When you see this symbol, you know that that equals some number. You may not know what number it equals, but you know that this equals, let's just call it x. Let's just say that. And we could say, okay, one way of thinking about this is to say, well, this means that some number times itself again is equal to 8. In other words, that's the output there. And we're trying to find the input there. Now, and this one happens to be, yes, 2, right? It happens to be the case that this is 2 right there. But if we didn't know that, right? Like if I just had this equation like this, and I don't know what it is, we don't really think about it. Like the way that we deal with this kind of equation is we don't say, well, what times itself times it. When you see this equation, you just go, well, I'm going to undo this thing right here. How do you undo something cubed? What do you do? I'm sorry. How do you undo the cube? Yeah. How do you undo the cube root of something?
You cube it.
You cube it. And so you, in this case, I guess, well, actually, you wouldn't really think about it this way. Let's give me a second to run into something else, right?
Please don't.
Put a pin in that because we're coming right back there in just a second. But the thing is, I know that this is some number. This number happens to equal 2, right? And so, say I had something else. Let's say I plugged in some number. Let's say 21 was my output. And we want to know, well, where did that come from? There is some number here that came from. I don't know what number it is, but we could say that this place right here is the cube root of 21. And it turns out that like we can't break this down anymore. 21 is 3 times 7. And so if you even tried to, like how we do where we pull out numbers from a root, we can't even do that here. We have 2 prime numbers. There's nothing that's going to happen there. This is as simple as it gets right there. But I think about that thing is this thing right there is some number. That number lives right here. He's bigger than 2. And the symbol that we use to represent that number is the cube root of 21. And we know that it's the case that this is some number. And if we take it and cube it, whatever it is, 2 point some stuff, if I take that and cube it, that is, if I multiply it by itself 3 times, and take that and go root 3 of 21 times root 3 of 21, whatever that number is, the thing that I'll get when I do that is 21. That's what that means, right? You following so far?
Yes.
Okay. Now, you already answered me this one. You said, what is this, right? So what this says here, if you think about this, my point for, my point for bringing this up, as we're going to see in a minute, is not every number comes out to be a nice, clean number, right? Like if I were to plug in the square root of 2 and then cube it, it's going to give me something really ugly that's not a nice round number. If I plug in 2 and cube it, I get a nice number. It's 8. Similarly, if I take 8 and take the cube root of it, I get 2. Beautiful. It's nice. Most numbers, though, aren't perfect cubes. Like 21, for instance, is not a perfect cube. And in fact, if you tried to write down the cube root of 21, it would take you infinity because it's a non-repeating, non-terminating decimal. It's irrational. And so the easiest way of writing it is with that symbol right there, rather than writing 2.817, wow, whatever the heck it is. It's just some number. That's a number. Okay, I just touching on that because we're going to see a parallel in a minute, but it's not really the takeaway point. I just want to have that on the board. The point, the interesting thing, the important thing that we're doing here is really this. This thing, what this means, it says that if you took some number here, let's call it X, and I'm just going to arbitrarily put it. I'm going to say it lives between, say, 1 and 2. Who cares? It could live anywhere. But if I take that number and then I cube it, that is, I multiply it by itself 3 times, I'm going to get out some number. What number is it? Well, X cubed. It's just, that's how we write that thing. It's X cubed. Okay, so let's think about this. I've taken a number. First thing I did, the first thing that I did to it is I cubed it. I plugged it into that equation. Now I'm going to take whatever number that is and pull it back by taking the cube root of it. It's trivial. It comes right back to where you started, right? It should come back to X. That's what you told me right here. When I said, what is this? You said it's X. Well, that's what we're doing. You take any number, X, it's 1.5. Plug it in by cubing it, 1.5 times 1.5 times 1.5. You get some number. Then you take its cube root. Well, you come back to 1.5. Like for instance, if I took the number 2 and I cubed it, and then I took the cube root, I shouldn't have to use my brain at this point. I shouldn't have to think about it. I should just be able to say, you took a number, you put it into a function, and then you pull it right back. You should end up where you started. And indeed, that's what you told me earlier, right? Right, when I first asked, what is that? You said it's 2. And it's because this is true, right? You know that, and that's another way that we kind of think about this. If I could turn this into, well, some number cubed, then I could just pull it right out. But that's what this means, right? It's because if you take 2, you cube it, you get 8. But then if you take the cube root, it just brings you back to where you started here at 2. Any questions so far?
No.
Okay, this should all be, you should be like, oh no, what's coming? Because this is all pretty straightforward stuff. And it is. And that's kind of, this is the point I'm getting at, is like, this is straightforward stuff. There's nothing new here. One more point I want to make is, suppose that our X lived up here. I'm going to put him right here. I'm going to say, let's say we have some number, X. In this case, he's a little bit bigger than 8. Okay. And let's say that I started by pulling him back by saying, okay, let's find first, we'll find the cube root of X. And so that number right there would be the cube root of x. And then I take that number, whatever it is, and cube it. In other words, I'm taking the cube root of x first, and then I cube it. What do I get? What do I get?
X.
X.
Yeah.
Right? And let's think about that. If we start with some number, let's say 8, and we take its cube root, and then we cube it. Well, let's just see. Let's actually take that cube root first. You already told me that the cube root of 8 is 2. Okay, nice. Okay, what's 2 cubed? 8. It's 8. It's exactly where we started, right? And we've seen that. You take 8, pull it back, push it forward. So the idea here is we have if we compose these functions, that is, we take the output of one and put it into the other, they're inverses of each other. So it's kind of like by definition, you end up where you started, right? Like if I start at 2, cube it, and then take the square root, I end back up at 2. If I start with something up here, if I start with 8, take its cube root, go down to 2, then I cube it. Oh, guess what? I end up where I started. You may not have realized, but you've been using this principle for a long time now. And it shows up like this. Suppose I had this equation. Let's say I had that equation. How would you solve that equation? What would you do?
I would cube both sides.
You would cube, and that's how you think about it, right? Because when I wrote that, that's what pops into my head. Cube both sides. Why do you cube both sides? Well, because it's the thing, cubing is the thing that undoes cube root. This says you took a number, yep, and you took its cube root, yep. But we want to get that thing back. I want to know, how do I get x back? Well, this is how you do it. I know that if I take this thing, whatever it is, and then I cube it, and so let's do that. Let's, just like you said, cube both sides. So we're gonna cube both sides. You don't, this is what you're using right there. You're saying, oh, wait a minute. I took a number, took its cube root, then I did the opposite of that, and it popped back the very number that I was looking for. 3 cubed, I believe, is 27. Because that's the same thing as 3 times 3 times 3. That's 9 times 3. And I believe 9 times 3 is 27. Yeah, it is. Okay. And so let's check this. Because what was my original equation? It said that the cube root of x is equal to 3. And let's just see if that works. I'm going to plug that in and see, okay, cube root of 27 equals 3. What does that even mean? Well, let's just think about it. If I take a 3 and I plugged it in, I would go 3 times 3 times 3 is 27. And then if I take the cube root of 27, of course, it brings me back to 3. Okay. So you haven't really realized it. You've been using this principle the whole time you've been in mathematics. Like when you solve for x, you undo things that have been done before, right? And so when you have an equation like square root of x equals 7, you go, oh, square both sides. Well, yeah, that's because the inverse of square root is square. Or if you have something like It's not. How about 49 equals x squared? You have it in your mind. I'll take a square root of both sides. Why? Well, because of this principle, right? If you undo the thing that you did, so I take a square root of both sides, then I come back to the number that I'm looking for. Does that make sense?
Yes.
Okay, so again, this is not new stuff. I'm kind of framing it in a different way. I'm saying it a little bit differently. But you know this stuff, and you've been dealing with this stuff for a long time. And so, okay, this is something that we want to figure out with logs and exponents. Okay, buddy, you could have some crackers. Yeah. So, yeah, here you go, buddy. Yeah, all right. So we want to, as you can see, like this principle right here helped us to solve equations. And that's very much where we're trying to go with all this exponents and logs stuff. And this, composing a function with its inverse, seems stupid. You know, I even said it like 5 times. If I take x and plug it in and then I pull it back, where do I end up? And you're like, x. Oh, well, what if my output was x and I pulled it back and then I pushed it forward? You're like, x. Like, of course, obviously, that's what it means. It's like, yeah, but then you didn't know that you were actually using that principle the whole time you've been solving these equations. So what we're going to do right now is figure out the analog of this principle, right? Because in this case, the nth root of x to the n is equal to x. That's how you compose those inverses. Or you could say if you had the nth root of x and then you raise it to the nth power, that's kind of how you get back to where you started. Or that's how one gets x by itself. And that's the idea. That's so much of what we're trying to do is get x or get something by itself. So we're going to get an analog for this type of thing with exponential functions. I want that up there so that we can see how these things work. So I'm going to do an exponential function, and it's going to be 3 to the x. This is the function that when I plug in a 0, I get out a 1. When I plug in a 1, I get out a 3. When I plug in a 2, I get out a 9, and so on. Okay. So now we said that, and I've already done it here, right? I've taken my 2 and I've plugged it into the function. This function, let me know when you have this written. I don't want to go on until you have this picture down.
Okay.
Okay, so let's take the number 2 and plug it into this function, and let's see what we get. So the function says to take 3 and raise it to this power right here. So I'm going to say 2 is my input, and my output is a 9 right there. Now you write this in log form. This is the exponential form. And we just went over how to write this in log form. This is log base something of something equals something. Ha. You tell me what it is.
Okay.
Okay.
Log base 3
Yep.
of 9
Mm-hmm.
equals 2.
There you go. In other words, right, look at this, right? When the input is 9, this is the function that brings you back to where you started. It says, well, 9 brings us back to 2, right? This is the function that says if you're at 2, we're going to go up to 9. This just reverses it, right? And in fact, and like here's another thing I want to say. Like we could just do this with any old number. We could say, kind of like we did before when we took a 21. 21 was not a perfect cube. And well, 7 is not a perfect 3 to something, right? Like I've already done the perfect ones. You plug in a 0, you get out a 1. You plug in a 1, you get out a 3. Plug in a 2, you get out a 9, and so on and so forth. 7 isn't a nice round number like that, but we don't need a nice round number for it. We could just say, well, what would that be? Well, it would be log base 3 of 7 in the same way as before. Get rid of this stuff here. And say that number, whatever it is log base 3 of 7. In other words, we're saying if 7 was the output of this function, then it must have come from this number right here, which is log base 3 of 7. There's something to notice, though. We just said, and I shouldn't have erased it. I was trying to give myself some room. We said that 9 equals 3 to the 2 means exactly the same thing as log base 3 of 9 is equal to 2. And so let's think about this composition thing. Now, just like there's some number between 1 and 2, it's 1 point something that this number is exactly equal to, right? So remember, what I'm doing here is trying to remember that this symbol right there is equal to some number. The same way as earlier, this 3, the cube root of 21 is equal to some number that's 2 point something, something, blah, 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 blah. This is just some number that's equal to, I don't know, 1 point something, something, blah, blah, blah. It's just a number. This number right here happens to be a nice round number, right? Log base 3 of 9 happens to, it's right, you have crackers right here. Log base 3 of 9 happens to be a nice round number, and that number happens to be 2. But check this out, and this is how we're going to compose something and get back to where we started. We know that 9 equals 3 to the 2, right? Obviously. But we said that 2 can be written in this funky way right here. 2, instead of writing it as 2, I could write it as log base 3 of 9. In the same way, like earlier, I could have said, well, wherever in my stuff that I want to have a 2 show up, I could write it as the cube root of 8, and it means exactly the same thing. So if I had the equation, say, 2 plus 1 equals 3, I could say, well, you know what? Forget about that 2. I could just replace that symbol with the cube root of 8 plus 1 equals 3, and it means exactly the same thing. Well, that's what we're going to do right here. We're going to say this symbol, 2, can be written as log base 3 of 9. And so I'm just going to replace it right there. And let's see what we get. 3 raised to the power of log base 3 of 9. And now look at what we have. our input was 9. And let's think about what we did here, right? Then I'm going to unpack what this means right here. Once you get it written down, let me know when you have this box thing written down.
Okay.
Okay, so what does this mean? Well, let's look at the innermost thing, right? The innermost thing is that 9 right there. What did we do? We took 9, which lived right here, and we said, let's pull it back with the inverse function. And so we did that. We said, okay, well, whatever the old output was becomes the new input. And we said that what this pulls back to is, well, whatever this is, log base 3 of 9. So that's how we got it back. Then we said, well, let's just take that and plug it back into the original function. So we took the number that we pulled back, log base 3 of 9, we plugged it back into our original function. Well, of course, it goes back to where you started, right? It's just like saying we took 8, we took its cube root, and it brought us down to 2. And then we cubed it. Well, of course, it went back to 8. Well, this is what we did here. We said, let's take 9, and we're going to take its log base 3. Well, that brings us down to 2. Because that thing is equal to 2. And then we said, okay, well, now we'll just take that and plug it back into the original function. So instead of going 3 to the 2, we're going to go 3 to the log base 3 of 9. So this is kind of like the analog there when I said, wait a minute, you're telling me that the cube root of 8 cubed is equal to 8? And you're like, yes, why are we going over this? Well, because look at what's happening, right? It's like you took a number, you pulled it back, and you got 2. Then we said, well, you don't need to write it as 2. You could write it as that pullback right there, the inverse of how did you get it. Then we said, okay, well, take that number and cube it, and you get right back to where you started. In other words, that thing and that thing always have to be exactly the same. And so that's what's going on here. We started with some output 9, and we said, pull it back. Well, it has that relation right there, log base 3 of 9. And that's kind of what I'm doing. I'm saying, well, let's keep it written like that instead of actually solving for it and figuring out what it is. We're just going to keep it written funky. That's what we did there. And then we're going to push it back forward. And we know that it has to come back to where we started. That this number and that number have to be exactly the same. Are you following?
I think so.
Okay. So now, crackers are right here. Look, right there. And so let's do the same kind of thing we did a minute ago. We said, well, in fact, before we get there, let's do it with that 7. Okay. So if we start at 7 right here, pull it back, we end up at, well, log 3 of 7, whatever it is, log base 3 of 7. Then if we push it forward, right, what should we get? So we pulled back log base 3 of 7, and then we push it forward. Where should we end back up?
3.
Started at 7, pulled it back, and now we're going to push it forward. Where are we going to end up?
7.
7. That's 7. Exactly. 7. And so let's finish this up, right? Because I mean, that's just all that means, right? We don't have a nice nifty symbol for what that is, right? That doesn't equal 2 or whatever, like it did in the other case where we said, well, if you pull back 9 and then push them forward, you end back up at 9. It happened to be the case that log base 3 of 9 was 2. And so we had a nifty way of checking that, kind of like how we did right here, right? It turns out that the cube root of 8 is equal to 2. And then we could check it and say, oh yeah, 2 cubed is equal to 8. Nice. Kind of like how we can here. We could say, wait, but log base 3 of 9 is 2. And so if I replace that with a 2, we get a 9. In this case, we don't have a nice round number. It would be kind of like if we had, in our original case, if we started with the cube root of 21, it's not a nice round number. But I know that no matter what, if I take that and cube it, I have to end up back at that number. So that's what we're doing here. We're running out of time again. So that's all we're doing here. We're saying you have some number, you pull it back. It's not a nice round number. It has some weird funky symbol. But when I take that number, whatever it is, and plug it back in, we end back up where we started. And so here's the big payoff here is, remember, we found that when you compose these two things together, you end back up where you started. And so get rid of this right here and do what we did before. We're going to say, let's suppose that any number was my output. Let's call it X. Now things are starting to get really ugly here, so I'm going to make some room. I'm going to take some number up here, X, and I'm going to pull it back by saying, where did you come from, X? So I'm going to do the inverse of that. And it's going to tell me, well, you end up at log base 3 of X. It's some number. It has a funky symbol, the same way as that does. Or when I plugged in an X, I get the cube root of X. Funky symbol, but it just means some number. Now I'm going to take that number, plug him into my original function, and I know that he has to come back to where he started. How do I plug this into my original function? Well, my original function says you take 3 and then you plug in whatever number this is up in the exponent. So I'm going to do that. Log base 3 of X is equal to X. In other words, right? We're coming right back to where we started. This is the exact same thing that's going on when we say, well, if you take the cube root of X and then you cube it, you end back up where you started. We could do this in the opposite. So are you following right now? Like why that's true?
Yeah.
It looks funky. I know. It looks really funky, right? But honestly, is it any more funky than this? Like we're used to it because we've done a bunch of these now and we've seen these for years, right? But now this looks really funky, but it's the exact same thing. You're saying you take a number, pull it back by a function, push it forward, you end up where you started. And then we had the other analog of this, right? We said, well, if you push it forward first, if you start here at X, push it forward with X cubed, and then pull it back. So in other words, start with X cubed, right? Then pull it back with the cube root. You also end back up where you started. So we could do the same thing here. We could say, okay, if I take some value X, plug it in, I get out, well, 3 to the X, whatever it is, it's 3 raised to the power of X. But then if I take that and pull it back with a log base 3, so let's see what I did. I took my number X and exponentiated 3 by it. So I took 3 to that power and it pushed it forward. And now I'm just going to take that and pull him right back. I'm going to say, okay, come back 3 to the X by saying, I'm going to take log base 3 of you. He's got to come back to X. So now we have this interesting composition. And remember what this did for us here? We didn't realize we had been using it this whole time. In order to get X by itself, we undo whatever had been done to X. And so if we had some equation that looked like this, the cube root of X equals 5, you'd say, well, cube both sides. Why do you do that? Well, because that's how you get that guy out of there. Same thing here. If you have x cubed equals 8, you'd say, well, take the cube root of both sides. Right, because doing that brings you back to where you started. This is how we get back to where we started, whether we started with plugging something into 3 to the x, or if we'd taken the log first by composing these things together. This is how we get our, I think about it as, this is how you get x to pop out, or the number that you care about. If you have an equation involving a log or an exponent, and it's like, I need to get something out of the exponent. How do I do that? Well, you undo exponent. You take the log of it. Or if you have a log and you need to get something out of that, you take the exponent. And so, are we good up to here? Any questions before we get our big formula for the day?
I don't think so.
Okay. So we're going to have to go over some actual examples in order to really make that, to see why this is good. But first, I want to say, okay, in general here, let's suppose we have the function a to the x. And we want to go in both directions here, right? So I'm going to say first, let's suppose that we have some number up here and we'll call it x, and it's the output. I want to pull it back and push it forward in order to give me a formula like this. And so what I'm going to do is I'm going to take my x and pull him back by saying, well, the opposite of a to the x is log base a. And so I'm just going to plug in my x. That's how I pull that guy back right there. Then I'm going to say, if I take that number and push it forward by plugging that number into here, well, take a to the and plug in a log a of x comes out to x. Got 2 minutes. Okay, so you're following that, right? You have some number, pull it back by plugging it into log, brings you back to where you started, or no, brings you back to the x-axis. And then you say, well, if I take that and push it forward with the same function, I end back up where I started. You good with that?
Yes.
Okay, so we're going to do it now in the opposite way and say, well, what if I started down here with some number, any number, call it x, maybe it's 5, maybe it's 22, who cares? I take it and plug it in and I go a to whatever that is. So like in our example earlier, a was 3. And so if I plug in a 2, we have 3 to the 2 is 9. In this case, I'm saying, okay, well then 3 to the x is 3 to the x, or in this case, it's not 3. We want to do it in general. We're going to say any base a. If I plug in my x, I get out a to the x. And then if I pull it back, I end back up at x. And so if I take this as my output and make it my new input and say, okay, I'll write it in the order that I'm saying it. We took a to the x, and then we took the log base a of that. It brings me back to x, brings me back to where I started. And we're just composing inverse functions. That's all we're doing. We're taking a number, using a rule to get a new number, and then we're saying we'll use the opposite rule to come back where you came from. And here you are. And we're going to see after they kick us off here in just a second, just how useful this is. We have equations involving this stuff. And in your home, I'll be explicit about this when I give you the homework. I want you to do these equations in 2 different ways. So for instance, we have this equation, log base 3 of x. is equal to 2. The first way I want you to deal with this is to turn the logarithmic equation into an exponential equation, which is what we've been doing all day. So you tell me how to do that. This means what in terms of exponents?
Okay. All right.
What?
In terms of exponents.
Yeah, we're just changing a logarithmic equation into an exponential equation.
Okie dokie. So you have x equals 3 squared.
I believe so. Let me double check. This is how I would think about it. I ask myself, what's the base? 3. And so I go, okay, 3. And then I go, inputs and outputs are swapped. So that's the old output. That's the new input. So 3 to the 2 equals that guy. And so yes. And so x equals what? What is 3 to the 2?
9.
Yep. And so x equals 9. Okay, that's how we do it one way. The other way I want you to do this is very similar to this right here. So taking aside for a second, and I think we actually did this one earlier. Suppose I gave you this. And I said, how would you solve this? What did you tell me? I'm sorry, he needs a crack.
No worries.
Yeah. Here you go, buddy. Yeah. So you told me that you would do what to this?
Cube both sides.
Cube both sides. Here's your crackers. And so you take the equation you already have and you cube both sides. In other words, what you did is you used that composition thing. Remember, like you took, oh, you had some x, you pulled it back and then you pushed it forward. And you know that that's how you get back to x by itself. And you get 2 to the third equals 8, etc. We want to get in the habit of doing the same thing here. And so in this case, we would say, well, let's look at this. It turns out that you had, you don't need to draw this out, I'm just doing this visually. You had 3 to the x. You had some output, we're calling it x, and you pulled it back with the function log 3 of x, and you got out a 2. Well, if we push it forward, that's how we get our x by itself. But how do you push it forward? Well, you push it forward with a 3 to the x. And so when you say cube both sides, in this case, we're not going to cube both sides. We're going to take both sides and undo them by going 3 to this side of the equation equals 3 to that side of the equation. And so we get log base 3 of x on this side, dropping those parentheses, 3 to the 2. And I want you to do these both ways. There's only 4 questions that you're going to need to do like this. One way you just translate it directly and then just calculate it. The other way is you actually solve it the way that you would solve it. Like you would say, well, how do I undo log base 3? Well, how do I undo log base a? Well, you take a and raise it to that thing. And so whatever you do to one side of the equation, you take 3 to that side of the equation, you have to go 3 to that side of the equation. And this, let's just look at our identity here. The same base makes whatever's inside pop out. And so we have that nice identity. In fact, we did that earlier, right? When we were working with 3. 3 log 3 makes x pop out. And so that gives us 3 squared. X equals 9. This is the way, this method is the way you're going to be doing these for the rest of your life. It looks funky at first, but it's way easier in the long run than simply translating it to here. But it's good to also be able to translate stuff and get it that way. Okay, so each one of these is, so back in the day when you had an equation involving a, let's say, a square root, you would get that square root all by itself, and then you would square both sides. In other words, you would undo whatever square root did. This is the same thing. You have some kind of, you have some kind of, in this case, it's always going to be log. And there, it's every single equation that you're getting, it's just log of something equals something. And the way to undo it is to exponentiate both sides. And so it's very much the same thing. I'm not going to go too much into that. So does that make sense, what I'm saying here?
Yeah.
Okay, so real quick, these are gonna, the X is not always gonna show up on the inside. Sometimes it'll be something like this. Log base 7 of 2 equals X. How do we undo log of something? Just forget about this, right? For your homework, you're only gonna be looking at how do I undo this thing? How do you undo log base 7?
So you have 7 log base 7.
Yeah, you would do something like this.
Yeah.
You would take both sides of the equation, and the reason that you do that is that it makes this thing pop out. Once you do that, that means, okay, whatever the input was is the thing that pops out. And so I just pulled this out of my rear, and you're not gonna be able to figure that one out. But this is like, but this is the idea. You're gonna have stuff like this right here. And this is the principle you're gonna use in every single time. And you'll notice that doing this, I want you to see this and do this. I also want you to reinforce this by saying, well, hold up, I could just write this as an exponential equation. And the exponential equation would say, okay, my base is 7. Yep. And it gets raised to the power of X. And the new output is the old input. And so it's 2. Oh man, it's the exact same thing. And it had better be. Okay, like, but you're not, you want to get in the habit of doing it this way, because trust me, it is so much easier to think about this in terms of just like the same way. Now you don't have to use your brain, you just go cube both sides, square both sides. Like that's what you do to it. That's what we're doing here. We're learning how to undo this, right? And so when you have something like this, it's like, oh, how do I do it? Well, you 7 both sides, take both sides to the 7, right? And so I'd like to see it both ways there. The last thing we need to talk about, it should not be too bad, is the, you're gonna get stuff that looks like this. So we also have this one right here. Log A of A to the X equals X, right? And that came from just taking some number X, plugging it in and pulling it back. And of course you ended up back at X. And so let's say, for instance, that, well, let's just do this. What is this? We shouldn't need to use our brains. Log 2 of 2 to the 7. What does that formula tell you that should equal?
7.
7. Let's just think about what this means just real quick. This means anytime I see a base 2, either in a logarithm or as an exponent, I think, okay, well, you're talking about the function 2 to the X. Either coming backwards or going forwards. That's what you're talking about. This right here says you plugged in a 7 and you got out a, well, whatever 2 to the 7 equals. I don't know what it is. It's a big number, but who cares? Because when you take that and pull it back, you end up at 7. And that's what you've done right here. You've taken your input 7, pushed it forward with 2 to the 7. And then you say, well, now just come back to where you came from. Just come right back. And there you are there. And so this makes calculation of these things very easy if you could get it like this. So for instance, if I had a log 7 to the 3, that would equal what?
3.
3. We really don't need to use our brains. This is the same thing as saying, hey, I had 7 cubed and then I took the cube root. Well, of course you came back to where you started from. That's what's going on here, right? That is what this does. It's the thing that does that. So we're going to do one of these. If I have log base 2 of, let's say, 4, I could say, I have no clue. That doesn't make any sense. But if I could write 4 as 2 to some power, 4 equals 2 to what power?
2 squared.
It's 2 squared. Oh, well, now I don't need to use my brain because this says you took a function and then pulled it straight back. This should come back to whatever the input was in this case. This is the 2. And so let's do one more. Let's say I had log base 10 of 1,000. The idea is, right, because of this nifty little fact, if I could get this number written as this number to some power, then my life becomes very easy. So how can we rewrite 1,000 to make my life easy? 1,000 is what to the what?
10 cubed.
Yes. 10 to the 3rd. There you go. And so log 10 of 10 to the 3 equals
3.
3. And so that's the, well, second to last part of your homework is it just gives you something like this. And right now, the trick, it says compute it, or it says simplify. But what we want is an actual number. And so the idea is if you could take whatever's inside and write it as this thing raised to a power, then your life becomes very, very easy because of this nifty fact. And it's exactly like when we were doing this type of thing, when we were saying, let's say, take the square root of 25. You say, oh, if I could write that as something squared, right? Square root, if you could write it as something squared, then you know that that just undoes what you just did. That's what we're doing here. Only instead of, it's a little bit different, but the idea is this right here. Push something forward with a to the x and then pull it right back, you end up where you started. And so that's the idea there. Any questions?
No.
Okay. Some of these in that section, they're gonna look it's not bad. It's not bad. You should be able to do it. It should not be a problem. Okay, so here comes your homework. Okay, buddy, give me just a second. Give me just a second. Get your cracker. Here, a cracker. Here, take them. Thank you. Okay, homework. Chapter 12, section 3 from page 528. All right, 528. Okay. 1 through 17, number 1 through 17. Odd. Number 19 through 25. And this is the one where I want it two ways. Right? And that's by explicitly solving the equation. Yeah, we'll call it raise both sides, right? Like it used to be, we say cube both sides or square both sides. Well, we're going to say raise both sides. So if you have log base 3 of x equals 2, then we're going to raise both sides. Raise both sides to the power of whatever that base is. And so that'll be 3 and a 3 right there. Okay, and that's what we did earlier. In fact, I think that's the same one we did earlier, right there, right? Solve it two ways. One, solve the equation via the raise both sides method. And two, translate to every one of these is a logarithmic equation. So we could translate it to an exponential equation, like you will be doing in 9 through 17. Okay, we don't need to do those. We are definitely going to do those though. So numbers 31 through 40.